This is ChainMind, the decentralized AI network built for everyone. Just search ChainMind on Google, sign up, download the app, and you're in. That's it. You've joined the network. Run it on any device, phone, laptop, or server. Why ChainMind? Fully decentralized, fully yours.
Imagine a computer in a car that can think a quadrillion times per second, yet fits inside a trunk and drinks less power than a household refrigerator. That is the headline that made the news, but the real story is how a single, purpose-built compute stack turns a fleet of robotaxis into a real-time perception engine, and why that blueprint matters for anyone building a decentralized AI inference network. Autonomous driving is not a single algorithm. It is a cascade of perception, prediction, planning, and control loops that have to fire in sub-millisecond bursts. When a camera spots a pedestrian, a lidar maps the surrounding geometry, and a radar confirms motion, a deep neural network fuses all that data into a semantic scene. Each step is a massive series of matrix multiplications, convolutions, and attention mechanisms that, until recently, lived inside data center GPUs. Moving that workload into a moving vehicle creates constraints no data center ever sees: a strict power budget, a tight thermal envelope, constant vibration, and the need for deterministic latency. The compute platform becomes the heart of the robotaxi, dictating how many sensors can be processed, how complex the models can be, and ultimately how safely the vehicle can navigate city streets. If the processor stalls for a single millisecond, the car could misjudge a cyclist's trajectory. If it overheats, the entire perception pipeline collapses. That is why Waymo's engineers focused on building a compute stack that could guarantee both raw throughput and predictable timing. Waymo's latest reveal shows a modular compute chassis that houses multiple custom ASICs, high-bandwidth memory, and a dedicated networking fabric. At its core is a tensor-first ASIC optimized for dense linear algebra rather than generic integer operations. The bulk of autonomous driving inference is matrix-heavy, so the chip packs thousands of low-precision multiply-accumulate units that run at 2-bit or 4-bit precision. After quantization, most perception models lose barely any accuracy, but the power savings are dramatic, cutting consumption by a factor of 3. Compared with a traditional GPU. The ASIC also integrates on-chip high-speed SRAM and a unified memory interface that keeps feature maps right next to the compute units, eliminating costly DRAM fetches that would add latency and waste energy. Around this primary accelerator sits a secondary processor dedicated to safety-critical functions such as braking and steering control. By separating hard real-time loops from the perception workload, Waymo guarantees that a sudden spike in neural network demand never jeopardizes the vehicle's ability to stop or swerve. This hardware segregation mirrors the way a pilot's instruments are isolated from passenger entertainment systems, ensuring that the most critical tasks have a clean, jitter-free path to the actuators. Delivering a quadrillion operations per second while staying under a 500-watt power envelope is a feat of engineering that goes beyond silicon. Waymo leveraged a cutting-edge 5-nanometer process, aggressive power gating, and a liquid cooling loop that runs through the trunk's chassis. The cooling system is co-designed with the ASIC so that temperature stays within a narrow band, whether the vehicle is cruising through a desert noon or idling in a snowstorm. Keeping the compute module compact and centrally located also reduces cable length, minimizes electromagnetic interference, and simplifies integration with the car's existing power distribution. The result is a tightly packed, thermally stable node that can sustain peak performance for hours without throttling. In practice, this means a Waymo robotaxi can process high-resolution feeds from 8 cameras, a 64-beam lidar, and multiple radars simultaneously. all while maintaining the deterministic latency required for safe navigation. Hardware alone would be useless without a software stack that can fully exploit its capabilities. Waymo runs a layered framework where low-level drivers expose a deterministic API to higher-level inference services. Those services are containerized, allowing engineers to push updates or A/B test new models without rebooting the entire vehicle. A central scheduler balances latency budgets across perception, prediction, and planning tasks. When the car approaches a busy intersection, the scheduler can allocate more tensor cores to the high-resolution front camera feed, then shift resources to lidar processing once the vehicle merges onto a highway. This elasticity mirrors the resource allocation strategies used in cloud AI platforms, but it happens on a single-edge device with hard real-time constraints. The scheduler also monitors power draw and thermal headroom, throttling workloads only when safety margins are threatened. By tightly coupling hardware metrics with software decisions, Waymo ensures that every watt of compute contributes directly to the vehicle's situational awareness. But here's the part most people get wrong: you don't need a massive data center to achieve that level of performance. The real power lies in specialized edge nodes that can work together in a mesh, each contributing a fraction of the total capacity. Waymo's Robotaxi brain proves that a self-contained, high-performance node can handle the most demanding perception pipelines. For decentralized inference networks like ChainMind, that validation is a game-changer. The lesson is twofold. First, hardware specialization matters. General-purpose CPUs and GPUs still have a role, but the economics of large-scale inference favor purpose-built ASICs that trade flexibility for efficiency. Second, a robust orchestration layer is essential to turn raw compute into usable AI services. A decentralized network must provide not only a token-based marketplace for compute but also a standardized runtime that can schedule, monitor, and reallocate workloads across heterogeneous nodes. Imagine a fleet of delivery drones, autonomous trucks, and personal vehicles, each exposing a compact, tensor-optimized accelerator through a unified API. Developers could offload heavy perception models to the network while keeping latency-critical control loops on device, exactly as Waymo does with its safety processor. The modular chassis, multiple ASICs linked by a high-speed fabric, mirrors the topology of a decentralized mesh. In a chain-mined network, each node could lend a slice of its fabric bandwidth to neighboring nodes, forming a collaborative compute fabric that scales horizontally without a single point of failure. The result would be a global AI supercomputer built from the spare compute cycles of everyday machines. Looking ahead, several challenges must be solved before a truly decentralized inference marketplace can match the reliability of a tightly controlled fleet. Security is paramount. Nodes need to prove they are running authentic models and not leaking proprietary data. Trusted execution environments and zero-knowledge proofs are promising, but integrating them with high-throughput ASICs is still an open research area. Model portability is another hurdle. Autonomous driving models are often trained on petabytes of proprietary data and heavily optimized for a specific ASIC. To enable a broader marketplace, standards for quantization, model compression, and hardware-agnostic graph representations will be needed. Finally, the token economics of a decentralized network must reward not just raw compute but also reliability, uptime, and compliance with safety regulations. Waymo's tightly controlled fleet shows the value of guaranteeing performance. Any public inference marketplace must emulate that level of assurance to attract mission-critical workloads. In the end, Waymo's disclosure of its robotaxi brain does more than showcase a marvel of engineering. It offers a concrete reference architecture for anyone building high-performance, low-latency AI at the edge. For Chainmind and other decentralized inference platforms, the message is clear: combine purpose-built, energy-efficient ASICs with a deterministic, safety-aware software stack, and you can turn a scattered pool of edge devices into a cohesive, powerful AI supercomputer. As autonomous vehicles proliferate and the demand for onboard inference skyrockets, learning from Waymo's design choices and extending them into a collaborative, token-incentivized network will accelerate the transition from isolated robotaxis to a globally shared AI inference fabric. If you want to be part of that future, follow Chainmind, join the conversation, and help shape the next generation of decentralized intelligence.